So this is the third part of my Southern Hemisphere DAC Sciences seminar series. This is without Antarctica, so explicitly ignoring forbidding Antarctica. And so looking at other parts of the cryosphere. Start out, this is this image of the world. Oh, wait, it is upside down. Here we go. This is the Southern Hemisphere view of the world. I think is always interesting to show. You can go to Australia or New Zealand and buy maps with the orientation like that with all the names in the proper alignment. So, but the thing that's interesting here, and it shows up a little better here, I think, is the Southern Hemisphere is dominated by the ocean, by the oceans. It's much compared to the Northern Hemisphere, particularly. Much less land in the southern region. If you take out Antarctica, it's even less. It's only about 13.5%, compared to about 40%, almost 40% in the Northern Hemisphere, 13.5% without Antarctica. And so, you have very different climate conditions. The other thing, this is, I know, a really bad projection. This is like a Mercator projection, and it's kind of a weird looking map, but I thought it was kind of cool because it basically flips the Southern Hemisphere onto the Northern Hemisphere with some displacement, but it shows you basically the distribution of the land relative to latitude. And I think you've got to take into account the big distortion with the Mercator projection, but even taking that account, there's very little land in the south of 45 degrees, south of the southern part of the Southern Hemisphere, just really the tip of South America, a little tiny bit of New Zealand, but yeah, all of Australia is more towards the equator than 45 degrees, and that's obviously again in stark contrast to the Northern Hemisphere. We're at 40 degrees latitude here in Colorado and Boulder, and really most of the Southern Hemisphere land would be more towards the equator for us. So yeah, whereas Antarctica has snuck in again, take care of them. But again, you can see when you look at the distribution of the cryosphere, it's the vast majority of the cryosphere is in the Northern Hemisphere. There's South America, little tiny bit in Africa. It actually cuts off South Africa there, which I'll talk about a bit. There is snow in South Africa, New Zealand, and then Australia, which I actually added in. They do get some seasonal snow there in Australia, in the mountains in Tasmania, and in the Blue Mountains, I think it is in Australia. But mostly, again, you can see here glaciers and seasonal snow cover is really what you get in the Southern Hemisphere. So I'll start out with snow cover. That is, again, you look at this and you see the vast majority of snow, where snow falls, is in the Northern Hemisphere. But interestingly, there was a article in the Washington Post a while ago that noted that Southern Patagonia has actually the deepest snowfall, the most snow accumulation on average anyways. And it's the Washington Post, US, so it's all in feet, but I did convert there for us scientists, over 50 meters of snow in the Southern Patagonia range. So they do get a lot of snow. You get the jet stream and a lot of moisture coming in off. You got, the whole Pacific Ocean there to build up, and it hits the mountains. So again, not a lot of area coverage by snow, but you can have some areas that get quite a bit of snow. I wanted to point out Snow Today, which is new, not new, but NSIDC website. Carl Ricker at Instar partners with us on this, and he and the Snow Today team released, this was back in February, so still relatively recent. There is now Snow Today tiles for New Zealand, and this is the most recent one from yesterday. Unfortunately, it's still kind of early in the season, so there actually isn't a whole lot of snow there. But you can see that it does have the data from 2001 up through the present, So you can see the range and variability covered, and that's basically the Southern Alps there. There is some snow that you get some snow in the mountains in the North Island as well, but this focuses on the South Island, which is where most of the New Zealand snow falls in the Southern Alps mountains there. Another product we have that is global, but includes the Southern Hemisphere, the NICE or NICE, near real time answer to sea ice concentration and snow cover extent. That's a passive microwave product. It uses the 18.7 and 36.5 gigahertz. It's now using answer 2, but it actually has been running for many years with SSMI and SSMIS. It's really nice because you get global coverage. Most of them go every day, and then it also has a 5-day latency to try to fill in anything that it misses. And it has owl sky capability, but there's some limitations. It's low spatial resolution. There's uncertainties for thin snow, vegetation. It doesn't really see topography very well or handle topography very well, but it does detect snow globally. And this is there's really not much to show for today. So I went back to last winter in the Southern Hemisphere, and again, you don't see a lot, but the pink there is snow. There's probably hard to see there, but the Andes has a fair amount of snow, and there's a little bit really hard to see in South Island of New Zealand. And we have the DAC snow products. These are primarily from Modus. There's several different products. Again, these are basically global products, so you can potentially get snow cover. And then also more recently now the Beers products. I didn't bother to show examples of those because I actually had another one that a colleague of mine at NOAA provided me. This is Peter Romanoff, who's at the City University of New York. And he works on some of the NOAA products, and this global multi-sensor automated snow mapping system. So the multi-sensor product does use Beers and Modus, as well as passive microwave data, and then going back AHR. And it merges everything together, so you get a pretty complete picture daily. And Peter has put together some really nice figures of some of the time series. And he graciously has let me borrow those and use these in the presentation. So a lot easier to use these than to try to put something together myself. But these are nice because they show the changes, at least over the last about 25 years. This is South America along the Andes. On the right, you have the mean duration of snow cover. Upwards of in the high areas, 200 days per year. And then on the right is the actual change from 2 decadal averages, 2005 to 2014 versus 2015 to 2024. And the red is less duration; it's lasting less. So the snow is melting off sooner or coming in later. And you can look at the snow extent. And there's a lot of variability through the year, but there's definitely a downward trend in both the annual average as well as in the winter. It's a little hard to see there, so I put in the units. This is, keep in mind, these are relatively small areas compared to what you see for the Northern Hemisphere. And then Australia and New Zealand, there's also been a strong decline in that as well, in the snow cover duration. There's also Australia there, which again, you can see how little snow actually there. It doesn't last particularly long, as in the blue, so it's like less than around 2 months or so. They do have some ski areas there, I believe, and New Zealand certainly does as well. And then you can see also there a little bit in the North Island, a couple of the higher mountains there. And again, snow duration, it's declining. Snow is lasting not as long. On the bottom, this shows like a nice the day-to-day in variability, and then the averages. Green is the earlier decade, 2005 to 2014, and then red. So there seems to be a little bit of a potential shift towards later snow cover. Not sure if that's really meaningful, but again, these are the smaller numbers, and so it's a small area. South Africa, does get snow. And in the higher, they have some higher elevations there, so they do get some snow, but it's quite small. Again, looking at the scale there, and it's quite sporadic, and it tends not to last very long. As I was putting this together, I happened to see that they actually had snow just a couple days ago, or last Saturday. Again, like a dusting on the mountains, but that's quite rare. You can kind of see there is a little spike there. So there's a little bit in April that they get, but most of it is in the June, July, August period. So, and they sometimes get snow in lower elevations. You can see pictures of cars and streets covered in snow, but it's quite sporadic. So now moving on to glaciers. That's really, kind of the biggest part of the ice cover, I'd say, in the Southern Hemisphere. I wanted to point out we have GLIMS here. This is a NASA product, NASA Earth Data product, help manage through the DAF. And it's primarily from satellite images. It's a database, especially Aster, but also other instruments. And it's an international collaboration. So NSIDC, the DAC manages it, but it also brings in groups and different glacier users and also providers of imagery and collaborates, and includes the Randolph Glacier Inventory. That's just a nice little picture cartoon that shows how things work. And this is just a map of the glaciers, of the glacial locations. These are all individual outlines, although they overlap there. And you can see, a lot in the Andes in South America. New Zealand has quite a few glaciers. Papua New Guinea has one, I think, or a small group of glaciers in high mountains. And then there's like two or three, including Mount Kilimanjaro in Africa. And those are, right up near the equator. But the mountains are high enough that they get enough moisture that they are able or have been able to maintain permanent ice there. You're talking about glaciers, a key thing, there's temperature. It has to be cold enough for long enough, but you also have precipitation. And so if you have more precipitation, cold precipitation with it being snow that can accumulate, even under, relatively warm, at least seasonally warm conditions, you can maintain glaciers, even near the equator. Another project, which is also a NASA, was originally a NASA Measures project. This was led by JPL, also folks at Alaska Fairbanks, and then Colorado here. Andy notes we are investing some new outlines for Puncak Jaya in Indonesia. Oh, thanks, Andy. Yes, so there are a few there, and that's also near the equator as well. So it's live. So this is looking at glacier flow and elevation data. It's able to process the data at low latency, uses Landsat as well as SAR data and Sentinel data. And this is it's global, but just pointing out the areas where they have data there. RGI is the Randolph Glacier Inventory. These are the RGI regions, they're called, I believe. And so again, South America, a lot. There are also, and I didn't point this out in GLIMS, you can see that there's some islands in the Southern Ocean area that one might say is outside of Antarctica, but there are glaciers there, like the Kerguelen Islands is one of those. I didn't share those before, but so there are a few scattered of those as well. This is an example. This is ice flow speed. The Upslope Glacier, maybe larger than X there on the map, so it's kind of the Patagonia and Southern Andes area. So they can collect the flow data, going all the way back before 2000. And there has been an increase in flow speed, which may indicate, again, warming and potential glacier loss. But a slight increase in flow speed, that's in meters per year, upwards of going up towards 2,500 to 3,000 meters per year. So kind of going and now looking at kind of the bigger picture of the changes that are seen that have been published from various sources. One is the glacier mass balance intercomparison exercise, GLAMBI. So this has taken a lot of different sources and put them together to try to measure the glacial mass change over time. And this is global. So the global figure is on the right, and the bar in the pink there is the annual deficit, or it's always a deficit globally lately, going back to 2000, or increase in the meters of water equivalent, and then the line is the actual cumulative loss in gigatons. And you can see, then I brought out the three, the Southern Andes, New Zealand, and then low latitudes, which is like the tropical, like African glaciers. And if you look at the numbers, they're, it's vastly different. The southern glaciers are a much smaller part of the equation, of the global equation there. But they are also, and they're a lot noisier in general. But generally there is an overall downward trend in the loss in glacier mass. So they're losing mass overall as well, like most of the world's glaciers. This is just another way, and this is a really complicated figure, which I won't go into too much detail, but the circles kind of give you a sense of what the relative, amount is, and then also the losses and percentage losses. So like New Zealand's lost almost 30% of its glaciers, which is pretty significant. Southern Andes, 12%, a bigger contribution, and then the low latitudes also quite small, losing about 20%, or the Southern Andes about 12.8%. So just another way to kind of show the change as well. But even though these glaciers in the Southern Hemisphere are not a big part of the global picture, they are quite important regionally. They're important indicators of change overall, and give you more of a global picture. But also locally, they're very important. One of the things is they act as essentially like water towers. They're storage for water and for water resources for communities that live downstream. You get the summer, the snow melts away, get towards the end of summer, the snow is all gone, but the glaciers are still there and still melting and still providing water. Up to 90 million people in South America rely on glaciers for water, and this is where it's particularly important in South America as a water resource. And then the loss of glaciers is starting to threaten that. Excuse me, if the glaciers go away, you suddenly don't have that late summer water resource. Another aspect, also particularly for South America, but glaciers can act as a dam. They form glacial lakes, essentially either from the glaciers themselves or from sediment from the moraines from the glaciers. Dams up water, forms lakes. And then with the glaciers melting, or either you can suddenly allow water to overflow and break through the glaciers, or the glaciers melting expose rocks and you get big rock slides that can fall into the lakes and kind of splash over the water. You get this what's called a glacial lake outburst flood, or Gulf, different than Gulf. But these have happened in the past. There was a big one in 1941, killed 4,000 people. There was a more recent one. I think that should be, no, that is 2025, yeah. So there was, just about a year ago, there was the Valinaraju in the Cordillera Blanc in Peru. You had a flood from a rock slide, and that's kind of a picture of the flow. And it flowed down, some outside of the city. It didn't go into the main part of the city in Juarez, but it did cause multiple deaths and destroy some structures. This is a nice, oops. Yeah, okay. This is nice little satellite image of it. Kind of a blow up there. You can kind of see, it's a little hard to see there, but there's the greenish blue there is the glacial lake. And then, so that was in 2024, and then this is in 2025 after that, and you can see where it's broken through, the lake is drained, and you see the debris field there. So compared to before and after there. So this is, as glaciers are melting more, losing mass, these become more of a threat over time, and more of a potential threat. So, there's this lack of water, but also too much water potentially in these regions. And looking at the elevation change, this is another way of looking at the glacier change in the Patagonian region, particularly. but also up through the Andes, the rest of the Andes as well. But lots of mass loss. The elevation change, it's dropping in elevation considerably over about 20 years there. And then the projections with continued warming, of course, is going to be further loss. And then on the far right gives you, the different scenarios, the blue being the most the best scenario, so to speak, and then the RCP 8.5 being the most significant. And so that's a loss relative to 2015. So under 8.5, about half the glacier mass would be lost in the southern Andes by 2100. It's another comparison. This is 1973, the Uppsala Glacier. It's the same glacier I showed earlier with the It's Alive, the velocity flow, and it's retreated upstream quite significantly in the last over the last 50 years. We see that with a lot of glaciers. So it used to fill up much of this fjord area there that is now retreated. So moving on to New Zealand, we also see losses there. The little inset is the main glacier area in the North Island, Mount Ruapehu, and then the Southern Alps there. And then that's the Tasman Glacier, which is, I believe that's the box for figure 3 there. And you kind of see basically the glacier is retreating and it's leaving this large lake in its wake as it's retreated over the last 60 years or so. We have some imagery from all the way back in the 1960s. So a big change in glaciers in New Zealand as well. And then this is showing the glacier length and starting again in the some of them are even before the 1960s. They're retreating the Tasman glacier up the top, and then some of the other glaciers, the box in the front, Joseph Glacier, and their Maori names as well, which I won't attempt to permit to pronounce here. But all showing losses, particularly at the Tasman Glacier, and particularly kind of accelerating in last couple of decades. And then looking at the future, this is looking at the glacier volume. Is the on the right is basically showing what happens to the glaciers under different scenarios. The red is the RCP 8.5, which is the strongest warming, business as usual, basically, no mitigation, high emissions, and then RCP 2.6 is there's strong mitigation, and you can see there's glacial losses, but if you go to the 8.5, you're looking at a large part of the glacier area in this area disappearing in New Zealand, and then the glacier volume, depending on the temperature, and this is interesting because it's actually, so it's percentage of 2020, and basically at 1 degree it goes up to about 150%, and that's because we already have warmed 1 degree, so or so, and so if we get to 3-4 degrees Celsius warming and global mean temperature, the glaciers in New Zealand will almost completely disappear. Mount Kilimanjaro, this is the big mountain in Africa, right just south of the equator. And the snows of Kilimanjaro, Hemingway, those are actually glaciers and snowfields, but there's a large number of glaciers, or glacial coverage at the top of the mountain, or there was. But it's been shrinking quite precipitously over the decades. This is over a century plus, from 1912. And you can see now, used to be, the glaciers ringed pretty much the summit, and now it's just in scattered locations. And so big losses there. And then that in the other low latitude glaciers also showing significant losses, like I showed before, and then with future temperature changes, getting about 2 to 4 degrees, again, they basically disappear in terms of your glaciers in the tropical regions. Another thing that tropical glaciers have been very useful for, but are threatened, is essentially as time machines. Ice cores. Ice cores, the Greenland, Antarctica, you can get some really nice ice cores going back hundreds of thousands of years, giving a long climate history. But those are at the poles or near the poles, and so you really want to have at least is some data from, in lower latitudes to see how the changes, um, how things have changed there as well. And so, one of the leading figures, Lonnie Thompson, at Bird Polar and at Ohio State, he was kind of the one that I think really started this way back. And him and his team, his wife, Ellen Mosley Thompson, is also very well known. They've gone out to many, many glaciers in tropical and mid-latitude areas to get these cores. They're not, they don't go back as far, the several hundred years that you get in Antarctica or Greenland, but they provide, really valuable to measure over tens of thousands of years potentially. And it's just showing from one of the papers, the delta 18 oxygen is basically an indicator of temperature. And so, it helps give a greater context to the global temperature changes. One of the interesting things I found, so, Lonnie Thompson, they go up high into the mountains to get to the glaciers. A lot of times they carry things in. It's pretty impressive. I've seen a couple talks that he's given. If you get a chance to see one of his talks, definitely good to do. But supposedly he spent more time above 18,000 feet elevation than any human in history. That's the theory. So he's well into his 70s. I think maybe like 80 or so. Yeah, I'm not positive exactly. But he had a heart transplant surgery in 2012, I think I remember seeing about, so at least 10 years ago. And he has gone back up into the mountains since then, I believe. I don't know if he's done it in recent years, but he's pretty impressive, pretty impressive guy. So, but this is just another, aspect of the glaciers that has been a really valuable resource. But again, these are disappearing very quickly. And they, along with taking these cores, they've recorded the changes that have been seen as well. And some nice pictures of that. And then permafrost, I haven't really mentioned permafrost because there's really not a whole lot to mention about it. The Southern Hemisphere, it's really very, very little. 99.6% is in the Northern Hemisphere. And there is in the Andes, there's a relatively large amount for the Southern Hemisphere. You do get some in Antarctica. This is exposed surface, so not under the ice sheet. So in like the dry valleys and stuff, that's permafrost. But again, it's orders of magnitude different from the Northern Hemisphere. So I just wanted to mention that, and I did find this paper that did actually quantify this, but it's a really tiny amount. The Southern Alps may have some, Kilimanjaro has some, again, where it's exposed, and then of course, again, Antarctica, but very little. And then one more, iceberg. This is coming from Antarctica, but it's escaped, and I talked about this in the last talk, the A23A. It's one of the longest lived icebergs. And they're nearing its end. I will give you an update on that. But it originally broke off in 1986. The Filchner ice shelf was roughly the size of Rhode Island. And it kind of sat there became grounded and sat there for 35 years and finally began moving northward, drifting northward in 2020. And it began breaking up in normal waters in December of 2025. This is an image from just after Christmas, day after Christmas, 2025 from MODIS, showing the iceberg. It's got the melt ponds on it on the surface, which is an indication that it's getting ready to kind of break apart. And so we've been kind of watching it, myself and some other folks, informally, and it was getting smaller. You can see the little chunks there breaking off. But the main part of it kind of hung in there longer than I think we thought it would. But by March, it had disintegrated down to about 100 square kilometers after a major pretty major breakup in that March. This is March 23rd. And you can see where it has drifted from, and where it's probably where it was on March 23rd. Yeah, the BBC there did a nice story on it with some nice visuals. And so, and then this is from Worldview on the right, that image. And then I look beyond that. This is April 2nd. It was down to about 60 kilometers squared, the main piece there. You can see all the chunks that are broken off and starting to drift away. And I looked more recently, and that was the last I could really get. I mean, you get clouds and stuff. So there was, I think, one other day, a week or two later, that I think I saw a piece of it, but it was so small that it was just like a little smudge in the MODIS imagery. So I'm not sure, but it went to 50 degrees south. So it's, that's outside of the Antarctic, I would say. So technically I can talk about this as not as a part of this talk, but that's getting into the warm waters, and it starts melting out pretty quickly. But again, it was a big iceberg that lasted for a long time. So that's it actually. So yeah.